Hello, good morning. Apologies, I'm not in with you today. I know it's obviously not seen you since last year, with having lockdowns being our first lesson back. And we've pretty much now finished this topic. I will be back in tomorrow though, and we'll go over a lot of the stuff on radioactivity and check that you are all feeling good about it and going for those top grades, which I know you can do, and we'll have a lot of time to go over it. So for now though, we're going to be doing lesson 5 in your booklet, which is activity and half-life. So turn to that lesson, I think it's page 25, and complete the do now. If you pause the video, you'll then be able to ask the questions, play the video to reveal the answers. You should now only be watching if you have completed the do now task. The answers are on the screen. You can mark your answers, so pause the video to mark them, and then we can move on. So we're now going to move on. So just a quick recap about radioactive decay. So radioactive decay, and the atoms will decay. If we get something that's radioactive, it is unstable, it will decay, and it is completely random. We cannot predict when an atom or a nuclei will decay. We don't know when it's going to happen. And we can observe it or detect it by using a Geiger counter. That's that thing that would click each time it detected a radioactive particle. Now they're always clicking because we've always got some background radiation around us. But if we hold it near a radioactive source, it will click more because it's detecting the decay from that source. Either as it's alpha, beta or gamma decay. And we measure radioactivity in something called becquerels. Becquerel, as you will remember, was the guy who worked with, or Marie Curie worked for him when she discovered radioactivity, and he got this unit named after him. So 1 becquerel is 1 decay per second. So on the Geiger counter, we will get 1 click per second, for example. So something might have more becquerels. It might have 10 becquerels, in which case 10 of the nuclei are decaying per second. Something might have 0.5 becquerels, in which case we're getting half a decay per second. So we get a decay every 2 seconds, that works out about. And that's how we measure it. We measure it in becquerels. So that radioactive decay is random. We cannot predict when a nuclei will decay. We just can't do it. We could try it, form sort of part of the basis of quantum mechanics. This not being able to predict when stuff is going to happen, not being able to predict anything. But we can make some assumptions based on probability. Because with a radioactive source, there are millions and millions, probably trillions of atoms within there. And by looking at that, we can use probability to work out how many will decay within a set period of time. We can't predict which ones it will be, but we can predict how many will decay over a certain amount of time. If you think, if you had a dice and you were to roll it, you couldn't predict what number was going to come up accurately. It would be really, really hard to do. But if you had 1,000 dice and you were to roll them all at the same time, you could probably have a pretty good prediction that about a sixth of them would be the number 1. A sixth would be the number 2, a sixth would be number 3, a sixth would be 4, a sixth would be 5, and so forth. If you had 1,000,000 dice, your prediction would be even closer, you'd be even more accurate. As we get more numbers of something, so the fact that the quantity of them increase, we can use that probability to predict it very, very accurately as to what's going to happen. And that's what we're doing with half-life. So a definition for you to learn. So half-life is the time taken for half of the radioactive nuclei in a substance to decay. So that's for them to turn from an unstable nucleus into hopefully a stable one, or sometimes a different unstable one. If you're not sure about that, look at the previous video when you're at home on the different types of decay. We're going to have a look at this graph here. You might see these graphs. So we've got on this bit here the number of radioactive atoms on our y-axis. And we're starting with 1,000 up here. And we've got our time going along our x-axis. This is in minutes. So we've looked at 1,000 of them. We want to work out the half-life. We need to see how long it will be until half of them have decayed. So we need half of this number to have gone. It's half of 1,000. That's right, it's 500. So let's find where 500 is. It would be about here. I'll just mark that on there. So we've got about 500 there, or it's 50% of the original value. And we find where it is on the graph. We've got this point here. And we can see that after 5 minutes, half of the nuclei have gone. We've gone from 1,000 down to 500. And let's have a think again what's going to happen next. So we're looking for the next half-life and seeing what's going to happen. So we're at 500 now. We want to have half of 500. What's half of 500? That's right, it's 250, which would be about here. I've got 250 radioactive atoms. Let's find where it is on the graph. We've got to here. What time are we at? We're at 10 minutes. Time from there to there is 5 minutes. We can see that each time we are halving the number of radioactive nuclei, the time is staying the same. It's taking 5 minutes to go from 1,000 to 500. It's taken 5 minutes to go from 500. Let's get the pointer. 500 to 250. Put it to the next one, it would be 125. We're down to here. That's taken up to 15 minutes in total from the start. And that again is 5 minutes from the previous one. So 5 minutes for half of what was left to decay. We've then got another 5 minutes for the next half to decay, and another 5. And we can keep going on. Now this type of decay is known as exponential. Exponential decay. Because the number that are decaying are decreasing and we're getting this curved line going down. Now I know all of you are too young to drink, but in a few years when you are old enough to drink and you decide to have a beer, if you get a proper beer, there's a good head on it, there's a good bit of foam on the top. If you leave that beer alone and don't drink it, the foam on that beer will decay. And it will decay similar to half-life. That first bit, so half of it will go in a period of time. That next half will go in the same period of time, and so forth. We'll see that decay happening even on a pint of beer. I know I probably shouldn't be talking about alcohol in schools, but I'm not in with you, and I'm hoping whoever is covering your lesson isn't going to report me. But it's just an idea of how this exponential decay works. We've got it in everyday life. But the important thing is the half-life is the time taken for half of the radioactive substance to decay. We can look at it and we can go, right, we start at 500, we're down to 250, we'll be down to 125, and so forth until we get down to 0. So we can use half-life to work out quite a few things. And we can use the half-life of different nuclei to calculate how old something is. The most common one we use is carbon-14. And we use that and we call it carbon dating. Now we're going to cross over into biology a little bit. So carbon-14 combines with oxygen to make carbon dioxide. This carbon dioxide is taken in by plants and they will, through photosynthesis, make glucose. So they'll make glucose This carbon is still the carbon-14, as opposed to carbon-12. It's still carbon, it's just got slightly more neutrons than our normal carbon. That is then eaten by animals, and it will stay in them. And the amount of carbon-14 in the atmosphere and in us remains pretty constant throughout our lives. It's there, doesn't cause us too much harm. But when we die, you'll see we stop eating. And the amount of carbon-14 begins to decay. Now, carbon-14 has a half-life of about 5,600 years. So after 5,600 years, when we would have had, imagine we had 1,000 atoms of carbon-14 in us, just over 5,500 years, we would have half of that number, because half of them would have decayed. So the count rate would be lower. It's generally constant, and as I said, it decreases as it decays. So it decays into nitrogen through beta emission. So one of the neutrons becomes a proton and emits an electron. But it begins to decay, so it can decrease as we're going through it. So we can work things out. So imagine we found a skeleton of a woolly mammoth, and we found it had about 50% of the carbon-14 atoms left. How long ago did it die? Well, if it had 100%, it would have all of them. It would have just died. But it has 50%. It has lost half of them. So we can say that it died 5,600 years ago. Why can I say that? Because it is one half-life. One half of those atoms has decayed. We've now got a skeleton of a caveman we found. It's got 25% of the carbon-14 atoms left. How long ago did it die? I've got 25% now. We need to think in half-lives. So, one half-life is 50%. Two half-lives, we've decreased it again, we're at 25. Sorry, 25%. Went to three half-lives, we'll be at 12.5%, and so forth, getting smaller and smaller. Oh, you need to go to 25% because I've got that one. So I need two half-lives. So it's died two half-lives ago. I need to work out two half-lives. So if one half-life is 5,600, I will do 2 times 5,600, and that will give me 11,200 years ago. And we can pretty accurately date a lot of things from a few years ago up until pretty much about 50,000 years ago, fairly accurately using carbon dating, so radioactive carbon dating, by looking at half-lives. So we've now got 3 questions for you to complete. Stretch and challenge one is question 3. Please do pause the video and have a go at completing them. You should now only be watching if you've answered the questions. Let's have a look at the answers. You can now mark your answers. Hopefully you've got all of these correct. If not, don't worry, we will go over this content and the rest of radioactivity tomorrow. Otherwise, have an absolutely fantastic rest of the day, and I will see you all later. Take care. Bye-bye.